Hello everyone, we are Group 1. This is our final presentation. Our topic is this, Neuromorphic Spintronics. Okay, first of all, I'll give you an introduction of our topic. My name is Chen Bingjun. And why do we need such like a neuromorphic system? Because nowadays we can see AI and ITO. They need large amounts of data computing, but their limited overall efficiency and calculation time due to data operation rules and transmission speed. And this require an improvement. So we found that the solution is to apply a neural-like system, which compute in parallel. And this can actually accelerate our AI computing speed. When it comes to our neuromorphic system, we need to compare these two, a real human brain and our modern computer. We can see that our brain show a lower energy cost due to its low precision calculation, and this is in parallel. And this rely on its low scale multiple parallel processing system. And on the other words, you can think that these are your intuition, common sense, and life experience. And our brain also stores information locally where it is processed. In contrast, we can see our computer solve their problems with relatively high precision. And this is a big disadvantage. The computer consumes substantial energy, shuttling information between its storage and the processor. This is our network look like. These two are our neurons, and the neurons are interact with this synapse. This is this is how our message in brain was delivered. And if we want to simulate this network, we can use transistors. But if we use transistor to act as our neuron and synapse, we need such like a lot of transistors. And this lead to large energy consumption and huge area requirement. So to solve this problem, we found that the Spintronic devices come in handy with non-volatility and the other benefits. This is a good one to emulate a brain. And Spintronic-based device can be more compact and energy efficient than the traditional one. This is our candidate for a Spintronic device. This is called MTJ, magnetic tunneling junction, and this is also non-volatile. And as a result, that's why our NRAM is superior to our DRAM nowadays. And MTJ also offers various functions by changing its geometry. So this is the figure show the structure of our MTJ. These two layers are made out of our ferromagnetic material and separate with a tunnel barrier or an insulator. Okay, so our goal we want to reach is we use Spintronic device to achieve the function of our neuron and synapse, which make our system can be more compact and consume lower energy. Okay, the rest will show you how their neurons and synapse look like.
I'm Jiawei, and I'll be talking about stochastic magnetic tunnel junction and spintronic memory states. So for stochastic magnetic tunnel junctions, I would like to introduce what is a magnetic tunnel junction. A magnetic tunnel junction, or MTJ, contains two ferromagnetic layers partitioned by an insulating layer with one side having fixed magnetization and the other side either parallel or anti-parallel to the previous layer. MTJs are also called binary magnetic tunnel junctions because they contain two ferromagnetic layers. So stochastic MTJs are where the magnetic tunnel junction undergoes stochastic switching or random switching. And basic MTJs are vulnerable to bit errors due to thermal activities. And these errors can be resolved by using various methods, such as adopting a junction with high energy barrier, which gives high programming currents, or error correcting codes, as well as specific write strategies. These methods, however, reduces the energy efficiency of the MTJ. And this diagram here shows examples of MTJ. And the paramagnetization can be thought to have low resistance, and the anti-paramagnetisation can be thought to have high resistance. And the binary property of MTJ is displayed by the 0 and the 1 here, in which 0 displays paramagnetization and 1 displays anti-paramagnetization. So for stochastic MTJs, they can execute spec timing dependency plasticity, or STDP. STDP is a biological learning rule where the strength between neurons in the brains are adjusted. And these SMTJs can help to reduce the memory required for tasks, leading to lower energy consumption during learning. And the diagram here shows an example of a stochastic switching of MTJ. So for spintronic memrisors, I'd like to introduce what is synaptic weights. Synaptic weights, or the connection strengths, in neural networks are non-binary. And many of the MTJs introduced earlier are required to store a single synaptic weight. There's a need to discover new storage for synaptic weights. And these storages should be continuous, non-volatile, and plastic. Or they can be have long-term properties and can be modified by inputs. Resistors with the above properties can be known as memristors. Here are some examples of memristors. And magnetic devices can also function as memristors, and they're called spintronic memristors. Here are 3 spintronic memristors shown. An advantage of spintronic memristors are that they can be able to have both learning and memorizing at the same time due to its non-volatility. And also can have an outstanding number of learning cycles. One challenge of a spintronic memristor is when we are scaling it down and when we want to maintain the same properties. We could do it by actually making the device smaller, or making the same device contain more magnetic domains for a domain-warm memristor, or having more skyrmions for skyrmion-based memristors. But it's very difficult to find the appropriate engineering materials. Thank you.
I want to talk about a spin torque nano oscillator, which is a candidate for the neuromorphic computing. And still know, structure-wise is exactly the same as the MTJ. And I think Jawed already talked much about MTJ. And the working principle is like this. We inject a DC current into the MTJ, and this DC current will be spin polarized by this spin layer, and the spin polarized current will give your free layer a torque, which make the magnetization in the free layer precession like this. And this precession will emit a microwave into the free space. But the power of the microwaves is too small, so if you want to collect them, you need a resonator or you need to couple them into the transmission line. So we usually collect the electrical signal as our output. And you can see if this is parallel, the resistance will be low, and anti-parallel will give the high resistance. So if your magnetization precession like this, the voltage will also oscillate like this. And this frequency is widely tunable by the input DC current and the external field. In the past, the TMR is too small, so this amplitude is too small, but owing to the recent development of MTJ, the TMR is large enough to make the amplitude robust to the noise under this nanoscale. And the behavior of this device is quite nonlinear in the memory. Nonlinear means the relationship between your input current and your output voltage amplitude is nonlinear. And the memory means your input signal can interact with each other, which means your output signal will not only depends on your input signal, but also depends on your previous input signal. And if you want to realize these two properties into a conventional CMOS, you need to integrate different components together, which will increase your device area. And for a simulation for neuromorphic computing, there's two approaches. One is the memory, just I previously said, and the other one is the strong coupling between your devices. Because STNO is highly sensitive to the neighbor mechanization dynamic, so they can strong interact with one another. Like your neuron, they can communicate with other neurons very well, and this is the experimental result of the researcher. He makes 9 different words and spoken by a different person and see whether their device can recognize the words said by different person. And you can see with the oscillator, the recognition rate increased a lot. And this is a map for a device. This axis is current, y-axis is external field. You can see with the increasing external field, your output signal amplitude will decrease because the precision will be confined by the external magnetic field. And in this picture, you can see once your current above the threshold current, the noise will increase dramatically, which also confirms the highly sensitivity toward external fluctuation. And this white block is the best working regime, which gives you the highest signal to noise ratio and the lowest error rate. To summarize, this STNO gives you higher integrated density and give you a good reliability, which means higher signal to noise ratio, and long lifetime means your input signal can interact with one another, and property 4 and 5, strong coupling with one another and highly nonlinear, is the same behavior as your neurons. And here's my reference. Thank you for listening. This time is good now.
Hello everyone, my name is Rudis and I'll be talking about the skirmion-based neurons and synapses. The skirmions are localized magnetic spin textures. They show particle-like behaviors, and in recent years they have been stabilized at room temperature by the action of stray field energies, higher order exchange interactions, and the DMI in multilayer systems. The skirmions can be accumulated in specific regions, which is very important for the neuromorphic applications. Another interesting feature about the skirmions is that they can be controlled by current pulses. That's why they have been envisioned as the next generation of magnetic memories. In this paper, they show how they are used as carriers of information, and they use a pin inside to facilitate the creation of the skirmions, and then they are pushed away by the current pulse. Skirmions could be used as artificial synapses in neurons. In artificial neural networks, the communication between the synapse and the neuron is represented by a sequence of current pulses or input spikes. When the membrane potential of the neuron is receiving all the signals from the synapses, it will increase its potential until it reaches a threshold. When this threshold is reached, then it will fire an output spike. Here we have a comparison between a biological neuron and a skirmionic neuron. In this paper, they proposed that they could mimic the leaking integrate fire functionality of the membrane potential by varying the position of the skirmion along a racetrack. In order to achieve this leaky integrate behavior, they optimized the thickness of the ferromagnetic layer and the heavy metal layer, obtaining a gradient in the perpendicular magnetic anisotropy. So whenever there's no current pulses pushing the skirmion towards the detection unit, the skirmion will slowly go back to the generation unit by the gradient in the anisotropy. They showed through simulations that skirmishes in a racetrack could perfectly mimic the leaky integrate fire functionalities of a neuron. On the other hand, we have the magnetic skirmion-based artificial synapses. In this paper, they took advantage of the nonlinear response in the change of resistance of skirmionic systems. So they accumulated skirmions in this synaptic area, and then they measured the whole resistance, and they could mimic the behavior of potentiation and diffusion of a biological synapse. So we can see here that just by changing the number of skirmions in this synaptic area, we could accumulate them or just dissipating them, and we can achieve the same behavior as a biological synapse. Then they proposed that an skirmion synapse device could be achieved by integrating the synaptic area into an MTJ. Using the 2T1R architecture cell, they could build an array of skirmionic synapses, making it promising for future technology. Thank you.
Welcome, ladies and gentlemen. My name is Zhou Bohen. Today I'm going to talk about the calculation of skirmions and challenges neuromorphic computing now facing. First, let's discuss about the computing with skirmions. The goal is achieving reservoir computing by skirmions. And allow me to give you two analogs for the reservoir computing. The first is the river is flowing. The river is referred to the signal, and the rocks in the riverbank is referred to the skirmions, and the water will thus have a different path. And the second analog is that we might have played the pinball game in the night market. The marble shootout is like the signal, and the stick patterns here guiding the marble is like the skirmions, and the drop area is the calculation result. And actually, I would say the magnetecture, like the different resistance area, is like the magnetoresistive material is the stick pattern. And for the second, I'm going to discuss about the simulation setup for reservoir computing by skirmions. Okay, skirmions are score-like particles, like this figure shows, and this is the practical setup for the reservoir computing, like remembering the rocks in the riverbank or the stick patterns in the pinball game. The water flowing force can push the rocks. In the reservoir computing, the spin orbital torque can also push the skirmions, and the application is the unconventional algorithms like neuromorphic computing. And the advantage is that skirmion is one of the smallest possible processing unit. And what is the overall advantage for the neuromorphic computing? Okay, first is the low energy consumption. The writing energy for the magnet device nowadays can be lower than 10 to minus 12 joule per operation. And the second is non-volatility. That means you don't have to keep refresh your device. And how to push this efficiency even harder? Okay, actually there are three ways to do it. The first is we can improve the spin torque efficiency, like we can enhance the water flowing force. And the second is like we can speed up our device in the writing and the reading. For example, using the parallel processing. And the third is like we can using anti-ferromagnetic material to reach terahertz of magnetization dynamics. And what is the biggest challenge the neuromorphic computing now facing? Actually, it is the interconnection problem. The artificial neuron nowadays could achieve most 1,000 synaptic per neuron. Does this sound great to you? And how about our brain? Actually, our brain could achieve 10,000 synaptic per neuron. But you might be wondering why we also don't fabricate this kind of order. Because due to the energy consumption is already tremendous in 1,000 order, not to mention 10,000 order. But there's one of possible solution is the skirmions. Why? Because using the reservoir computing, like to simulate our brain working, it might serve as one of the solution. But to fabricate high quality and stable skirmions, there is a long way to go. And this is the end of our presentation. Thank you for your listening.